Hello, Dr. Spalding here. Today we're going to be focusing on transformations of functions. The standard that we're working with is graph and describe the effect on the graph of f of x plus k, f of the quantity x minus k times f of x, and f of the quantity k times x for specific values of both negative and positive values of k. The learning intention is we will learn how positive and negative values of k transform a graph f of x for f of k plus x, f of the quantity x minus k times f of x, and f of the quantity k times x, so we can apply transformations to trigonometric functions. Success criteria are by looking at the equation of a transformed function compared to the parent function, I can identify horizontal stretches, horizontal compressions, reflections over the y-axis, horizontal translations, vertical stretches, vertical compressions, reflections over the x-axis, and vertical translations, and I can anticipate how the graph of a transformed function will look. So for this recording, we're going to look at the parent function f of x equals x cubed, which we have right here. This is an odd function. It has rotational symmetry about the origin. So if I rotate this 180 degrees about the origin, it will look exactly the same. We're going to start by talking about horizontal stretches, horizontal compressions, and reflections over the y-axis. And that is when you are in the form of f of the quantity b times x. B is a real number. So right now b is 1. But if I make b -1, then we get a reflection over the y-axis. So you can see with our new graph in blue, it is a mirror image compared to the red graph over the y-axis. So when b is negative, it creates a reflection over the y-axis. Now, if the absolute value of b is in between 0 and 1, so let's say we'll make this 1/2. Then you have a horizontal stretch, in this case by a factor of 2. So let's talk about some points on the original parent function f of x equals x cubed compared to our transformed function. So we have the point 1, 1 on the parent function, but for the same y value, the x value has been multiplied by 2. So on our parent function, there's the point 1, 1. On our transformed function that has the horizontal stretch, we have the point 2, 1. 1 times 2 is 2. Or another example, we have the point 2, 8 on our parent function. So for the same y value of 8, the x is going to be multiplied by 2. So we have the point 4, 8. That's 2 times 2 is 4. Let's see what happens when we multiply x in parentheses by a third. We still have that horizontal stretch. But now, for the same y value, the x has been multiplied by 3. So here's the point 1, 1 on the parent function. For the same y value of 1, the x has been multiplied by 3. So instead of 1, 1, we have 3, 1. 1 times 3 is 3. Or if we go back up to 8, we had the point 2, 8 on the parent function. Now on our transform function that has been horizontally stretched by a factor of 3. For the same y value, the x value has now been multiplied by 3. So instead of 2, 8, we have the point 6, 8. 2 times 3 is 6. Now, if the absolute value of b is greater than 1, then you get a horizontal compression. So let's say that b equals 2. So you can see in blue, we have a horizontal compression. In this case, by a factor of 1/2. So let's look at the point 1, 1 on our parent function again. Because we have a horizontal compression by a factor of 1/2, that means that for the same y value, the x value is going to now be half of that. So instead of 1, 1, we now have 1/2, 1. 1/2 times 1 is 1/2. Or if we look back, we have the point 2, 8 for our parent function. So for our compressed function, the x coordinate is going to be multiplied by 1/2 for this same y. So instead of 2, 8, we now have the point 1, 8. 1/2 of 2 is 1. All right, so you can see whenever b, the absolute value of b is in between 0 and 1, you have a horizontal compression. I can also make this -1. So this one has a reflection over the y-axis and a horizontal compression. Okay. Then when the absolute value of b is in between 0 and 1, in fact, let me put 0. And I'll do 0.999. So in between 0 and 1, not including 0, not including 1, then you get a horizontal stretch. And I can do the same thing. I'm going to change this to negative and this one to negative. Oops, I need to make sure I'm in correct order here. So now it's a reflection over the y-axis and also a horizontal stretch. So what does this look like if we were to write these transformations with our cubic function? So below is an example of a reflection over the y-axis. So you have y equals, in parentheses, negative x cubed. So f of x equals x cubed. So whatever you put in these parentheses in your function notation, you're going to replace x with that in parentheses. So we have negative x in parentheses cubed. Let me get rid of this. There it is. Then example of a horizontal compression, that's when the absolute value of b is going to be greater than 1. So we have y equals, in parentheses, the quantity 2x all cubed. So there's a horizontal compression. And here's an example of a horizontal stretch. That's when the absolute value of b is in between 0 and 1, not including 0, not including 1. So y equals, in parentheses, the quantity 1/2 all cubed. And it creates a horizontal stretch. Now let's talk about horizontal translations. That is when you're in the form f of the quantity x minus h. So when h is positive, and remember h comes after the minus symbol, x minus whatever the value of h is, then you have a horizontal translation to the right of the parent function. Then, if h is negative, you have a horizontal translation to the left of the parent function. So below is an example of a horizontal translation based on our parent function f of x equals x cubed. We have y equals the quantity x minus 2 cubed. This is a horizontal translation to the right because the value of h is 2. It comes after the minus. So we go to the right 2 units. Let me take this one off. You can see we translated to the right 2 units. And then next is an example of a horizontal translation to the left. We have y equals the quantity x plus 2 cubed, because x plus 2 is the same thing as x minus negative 2. So the value of h would be negative 2. So since h is negative, it moves to the left 2 units. Next, vertical stretches, vertical compressions, and reflections over the x-axis. That's whenever we have a times f of x. So if a is negative, you have a reflection over the x-axis. So you can see this graph is reflected, it's a mirror image over the x-axis. Now you might notice it looks exactly the same as what we did whenever we had a reflection over the y-axis. And that's because this is an odd function where f of negative x equals negative f of x. So I'll show you that in a little more clearly in just a moment. Okay. Now, when the absolute value of a is greater than 1, then you have a vertical stretch. So let's take a look at what that means. I'm going to make a equal to 2. So that is our green graph here compared to the red graph of the parent function. If we look at the red, we have the point 1, 1. If we look at the transformed function that has been vertically stretched by a factor of 2, that means for the same x-coordinate, the y-coordinate is now going to be twice as high. So instead of 1, 1, on our transform function, we have the point 1, 2. Because 1 times 2 is 2. Or we have the point 2, 8 right here on our parent function. So for our transformed function, we are going to have the y-coordinate be twice the y-coordinate of the parent function. So instead of 2, 8, we will have 2, 16. So I'm going to zoom in to make it a little clearer. And you can see there is a point 2, 16, because 2 times 8 is 16. All right. Now, if the absolute value of A is greater than 0 and less than 1, then you have a vertical compression. If I use 1/2. Well, let's look at the parent function in red again. It has a point 1, 1. But now we did a vertical compression by a factor of 1/2. So for the same x value, the y value is going to be half that amount. So instead of 1, 1, we now have the point 1, 1/2. Or here is the point 2, 8. But since we did a vertical compression by a factor of 1/2, for the same x value, the y value will be half of that. So instead of 2, 8, on our transform function, we have the point 2, 4. Half of 8 is 4. Okay. So for values of A that are greater than 1, you have a vertical stretch. Sorry, I needed to change this. Let me change this to 1, not 0. Let's play it again. So vertical stretch for values greater than 1. I could also change this to negative values. So values that are less than -1. You'll have a reflection over the x-axis in addition to a vertical stretch. Next, if the absolute value of A is greater than 0 and less than 1, then you will have a vertical compression. So you can see the vertical compression. I can also do the same thing. That it's the absolute value of A is greater than 0 or less than 1. So I'm going to go from negative 0.999 to negative 0.001. So we have a reflection over the x-axis as well as a vertical compression. Okay, so let's talk about what that looks like with our function y equals x cubed if we were to actually write it out. So below is an example of a vertical stretch, y equals 2 times x cubed. So you're multiplying the function by 2. So the 2 is not in parentheses with the x cubed. You're multiplying the original function x cubed by 2. So y equals 2 times x cubed. Then below here is an example of a vertical compression. So again, you're multiplying the parent function x cubed by 1/2 in this case. So there is an example of a vertical compression. And below is an example of reflection over the x-axis. So here is a function x cubed. You need to multiply it by a negative value. So the negative is not in parentheses. Change the color. So you can see that's an example of what the equation looks like with the reflection over the x-axis. But I want to go back up here where we said that this was a reflection over the y-axis. In green, and you see it's exactly the same. Again, that's because for this example, this parent function is odd, and what we have in green is f of negative x, and you see that equals negative f of x. Then our last transformation would be vertical translations. That's when you have f of x, and then you add k on the outside of the parentheses. So when k is positive, then you move up k units. When k is negative, then you move down k units. So here's a vertical translation up when k is positive. So it's above the original function in red. And then here, the vertical translation down, it's below the function in red, the parent function. So an example of writing a vertical translation up. I could write y equals x cubed plus 2, and the 2 is not in any parentheses. That makes me have a vertical translation up 2 units. And then an example of a vertical translation down, have y equals x cubed minus 2. You can see we have translated the graph down 2 units, and the minus 2 is not in parentheses.